Hey guys, what's up? Eddie Aho here with KissAnalog.com. Today we're going to start our switch mode power supply series. We're going to start with the buck regulator, okay? And to kind of start this thing off, I think we're going to compare it to a linear regulator, as they're kind of similar. And so today I'm going to go through an explanation of why we use a buck and what it does, okay? So I'm going to pull up my whiteboard. And there we go. There's our buck regulator. Well, actually, this is our linear regulator. But the linear regulator, you know, an LM117, it's an adjustable linear regulator, so it has some feedback. So basically it's shown like this, an in and an out with an adjust pin tied to two resistors to get feedback. You set these up so that you get the right voltage here, and then it gives you the voltage you want out. Okay? So let's say in this case we have 12 volts and 5 volts out. So if you need 1 amp, then you need 5 watts on the output. Okay, great. Well, if you have 12 volts here, then you're dropping from 12 volts down to 5 volts. And linear regulators are great because they're easy to use, but they're not very efficient if you have a situation like this. Now, if this was 1 milliamp, awesome, great, use a linear regulator. If you're not dropping very much power, then use a linear regulator because, you know, they're simple, they're clean, and simple and clean. But if you're not dropping very much power, there's no reason to use a switcher. Switchers are to save power for efficiency, okay? So let's take a look at what we're talking about here. Alright, we're back. Magic. So if we have 1 amp on the output on a linear regulator, it means we have to have 1 amp on the input. And if we have 5 watts out here, 1 amp times 12 volts, we have 12 watts coming in. So 12 watts coming in to get 5 watts out. So we're dropping 2 problems here. One, we're dropping 7 watts on that linear regulator. That's a lot of power, so that may not work. If it's one of those big old metal cans and you're going to put a big old heat sink on it, that's still going to be really hot. You're probably going to still need a fan, and that's still pushing it. Efficiency is only 42%. So that's where we run into a problem with linear regulators. You know, today, it seems like to me, every linear regulator is referred to as a LDO, low dropout regulator. But let's take a look at that for a moment. Alright, so I kind of drew what this might, you know, it's kind of a simplified version of what's inside this regulator block. You know, this kind of dashed line. You'd have a transistor with a gain stage and a place to bring feedback in. So you have a reference voltage maybe on this amplifier, and this this feedback is compared to that and drives the transistor. Now, it could be an NPN where you need, you know, typically on a regular linear regulator, you need a couple volts higher on this side so that this thing can regulate properly. Well, along came the LDO a long time ago, and one way they do that is, say, instead of use an NPN, use a PNP, okay? So that way the arrow points to the base, and instead of having to have a 0.7 volt drop here, the output can actually be 7.7 volts higher than the drive signal. So you can get a lower drop this way. There's other ways to do this, several ways, but that's referred to as an LDO because you don't need as much dropout voltage. Here you require a certain voltage to make it regulate. They call that dropout. Here you need it too, but less. So it's low dropout. And then they even have, you know, they've even improved those. But everybody seems like refers to regulators. I mean, not everybody, but you know, it seems commonly that we're calling linear regulators LDOs. It's just kind of thrown around all the time. Not all linear regulators are LDOs. Just want to make that point. In this case, 12 volts to 5, it's a waste of money to buy an LDO, right? Because you're dropping lots of volts. And so you don't always need an LDO. Just want to kind of hammer that in there, because you know, if you are, say, going from 5 volts to 3.3, that's still probably not even a case where you need an LDO. Maybe you're on the border. Let's say you're going from 3.3 to 2.5. Well, yeah, now you're getting to where you need an LDO. That's kind of why they came up. And then 2.5 and 1.8, yeah. So in those cases, you need an LDO, okay? But again, if you're dropping enough power across those, even in an LDO, if you're, you know, pushing some current and you only have, say, a 0.7 volt drop or half a volt drop on a LDO, well, and if you got 1 amp, you still have a half watt. Now maybe that's okay. So at some point there's a breaking point where you need a switching regulator, something more efficient. So let's take a look at that. Alright, so just before we jump into the buck converter, I just wanted to go over, you know, a better case scenario versus this. Kind of a worst case, 12 to 5, say 5 to 3.3. Hey, that's only 1.7 volt drop. With 1 amp, you still, you know, you're going to get 3.3 watts out here. You still have 1.7 watts that you're dropping across your regulator. That's a lot of power still. So, and it comes out to 66% efficiency. Not so great. So, still not a good thing. That's still too much. So, along comes a buck converter. Now let's take a look at that. Alright, so I kind of drew a buck regulator here. Kind of simplified it. Not quite done, so hold on if you see things missing. But up here I did not show capacitors on the input and output, but linear regulators, you still need capacitors, right? Okay, and then on this I am showing the capacitors because we know switchers, they're very important to have good quality capacitors. Alright, so basic function. Transistor turns on and off. You have 12 volts. Instead of this guy where it's linear, where it's just kind of amplifying it, a lot like an audio amplifier, right? It's linear. It's in this case, it's on or off. So if it's on, you got 12 volts here. If it's off, 0 volts, right? So if you have a 50% duty cycle, then the average is 6 volts. You know, you just kind of imagine these peaks and everything all filled with water or sand, and then the side wall is falling. It kind of levels off to about 6 volts, right? So, alright, 6 volts on the output. Efficiency on these switchers, you know, we'd have to do some math. You get some losses here and that, but really, if the switcher is on, you know, without any switching losses, you still have some DC resistance in your inductor. Now you need this inductor to smooth off, you know, to filter this out so that you get a DC voltage over here, right? So that's what the LC is for, big part of it. So inductors don't like to change current quickly, right? So when this guy's on, it ramps up to the inductor and then it ramps back down. So it smooths it out, and then the capacitor gives you that nice smoothed out DC voltage. You're going to get some ripple on there, you're going to get some noise depending on this, you know, how clean this guy's operating. But okay, but efficiency, now it's just taking in DC losses, so resistance losses through your choke, and yeah, you're going to get some losses through your capacitor switching elements. But yeah, your efficiency is going to be high. So the losses on this are, let's say if it was only 90%, you'd have 10% of your losses. So if you had, same case here, 12 watts here, then you'd have, you know, 10% of 12 watts, which still 1.2, but way better than 7. But also 90% is low. It's going to be high. It's going to be, you could be 97%, 98%, let's say. So you only have 2 or 3%. So you're going to have low losses here. All right? And they're not all on the transistor. They're spread around on the inductor and transistor mostly. Okay? All right, let me show you something else that I left off here. Okay, so I think the first picture, just showing you a duty cycle and how the average on time gives you your voltage output. Well, so if you really wanted 5 volts, you wouldn't have an on 50%, right? It'd be whatever ratio that is less than 50%. And then, you know, you get your 5 volts. Well, we're going to go into the design of how these things work and simulation, all that stuff in another video. I just wanted to make this a quick intro of, you know, the difference, why you'd use a buck over a linear. If you're dropping any power, you want to use a buck regulator. If you're not, use the linear. And this diode, that's an important function. You know, this portion here, the on-off, the duty cycle ratio, I think that makes sense. Hopefully that part makes sense to you. But, you know, imagine if it was only on 10% of the time. You'd have 10% of the voltage, 1.2 volts out, roughly. I mean, you get some drop across your inductor and across the transistor, you know, because there's that resistance on. So if you needed 1.2 volts out, instead of 10%, it might be on like 10.5% or something like that. So, you know, duty cycle, the percentage gives you your percentage of your voltage out. But now, this is where the magnetics and the interesting things come into play. You have to have a diode in here. They call that a freewheeling diode, or a reset diode, or a flyback diode. That diode, that inductor, remember when we were talking, doesn't like to have current change quickly, right? So when that transistor turns on and applies 12 volts here, then this guy, he's like, well, okay, great, 12 volts, I'm not going to let current just rush through me. He lets it ramp up linearly. So the current comes up like this in this inductor, and then when this switch opens, current stops ramping up. Now it starts to ramp down. And if you don't have a closed loop, how does it do that? So you have to provide this guy, which is a switch, right? He's off when this is plus, and relative to the what I'm showing is a ground symbol, the return. But when that switch opens, then the polarity in the inductor switches. So you get, and that's where you get that kickback voltage on relays and that. So if you had 12 volts here, all of a sudden you get 12 volts here, it switches, and then the current starts to ramp down. Well, when it does that, it goes through this capacitor and even the output, and it comes back this way through the inductor, and it allows that path to still have current flow. Otherwise you'd get that kickback energy, and it could go really high in volts. In this case, it's limited to the 12 volts, and it just continues that ramp. So you get a ramp up, you get a ramp down, okay? Another interesting thing about these things, what if you didn't have enough load out here? You're not pulling a lot of current. Well, if you're not, then you only get a little bit of current going up, whatever you need to keep the voltage regulating, and then it drops back down. And then you wait until you get another pulse. Well, between that time when the current ran out, it kind of equalized, came to equilibrium, the inductor is no longer, you know, circulating current, then it's sitting there waiting for another bump in voltage, and this guy turns on, bumps up the voltage, starts it over again. But that dead time in between is what they call the discontinuous mode, which makes sense. It's discontinuous. It's not continually providing current. It's sometimes it's in equilibrium. I call it when the inductor runs out or runs dry. So no more water in it, right? It's run dry. It's just sitting there waiting for another. Often we like to run them continuous. So if you're going to run continuous, you have to have a certain amount of load here, so that so your current level's up a little bit higher and you can keep current. Another thing is to switch faster. So the time in between, even if it's 50% duty cycle, if instead of running say 100 kilohertz, you're running say 1 megahertz, well, it's 10 times faster. So that time off is 10 times less. So that helps you solve that problem too. What's the problem with discontinuous? Well, there's some control things, right? It's kind of like if you're pushing a car down the street to the gas station, and you know, you get a big old push and it starts to roll and then it stops. Then you get all your guys behind it, you push it again, and every time you're kind of pushing from dead stop, dead weight. Where if you just kept it going, like you got it going, then you got tired and let it slow down, but before it stops you go, okay, got to get going again. it's easier, right? You can imagine that. It's easier to keep it going. If your output is just running here, no load, and all of a sudden it needs a load, like a step load, well, it has to fill this inductor up with current. You know, you got to get some power there, and so that it can relay that power every cycle. And if you have some continuous current flow, it's just easier to do that versus everything at a standstill and then you punching it. So as far as your, you know, your control loops and stuff like that, it's a little more complex. Continuous is just simpler. The ripple current in these capacitors is going to be higher too when you are running. So that brings up another thing. Often when people are designing these, they think right away, well, what do you know, what ripple current, how much ramp do I want versus my average current? And people come up with numbers like 20%, 30%, 40%. You know, I'll let my ripple current be 20% of my overall average current coming out. Or I'll be 40 or 50%, you know, something like that. There's these ways to optimize your circuit by coming up with a percentage, you know, and so if you come up with this percentage, then you go, wow, okay, that ought to run optimally. But if you do that just based on your max current, if you do it based on your nominal current, you might have trouble with your max current. But if you do it based on your max current, then what's going to happen on light load? You could end up being discontinuous. So really, you have to, before you decide on what percentage you want based on what's optimal, you have to decide what your circuit's going to do, what your minimum load is, what your maximum load is, and how you want it to operate during that range. So it might not come out, let's say if somebody's telling you 30% or 40% is the optimal ripple current based on your max current, well, that might not work for you if you drop down to 10% load. So we're going to talk about that. We're going to have some design examples in the next video, okay? But just want to point those things out are the considerations you're making when you're coming up with how to design one of these things. All right. Another thing to think about is this inductor. It's charging up current, right? It's charging. Well, if it gets high enough in current, the peak value where this guy saturates, well, then you're going to get this. When it saturates, current instead of ramping up this way, it's going to just fly up. Well, that could, see, one thing I haven't shown is the controller for this FET. He's got feedback coming over here. So over here it's simple. Maybe just goes into a little gain stage. Over here there might be more to it. There's going to be more to it, of course, because there's got to be something to controlling the on-off time. But also, it's going to be looking at current, you know. And so as current's going to this transistor, if all of a sudden the inductor ramps up because it's saturating, it's going to hit the overcurrent mark, hopefully. If not, you could have problems. You could burn up this guy. So this guy has to be selected that at the peak current that you're ever going to put through there, the max current, that he's rated for that, where the field's not going to collapse. And basically when that happens, it's like the inductor's shorted, okay? So you don't want that to happen. So, all right, and then the other consideration for this is just during normal operation, there's going to be DC resistance in this, and you want to calculate that out so that he doesn't get too hot. And vendors, it used to be for, like, especially for military stuff, you don't want it to get more than 30-degree rise. Well, sometimes they rate them at 40 or 50 degrees, so you have to look at when they say, when you're comparing two inductors, and one says, hey, it can handle 1 amp max current, and another one can handle 2 amps max. Well, the 2 amp max might be because it allows the temperature to go up to 50 degrees, where the 1 amp might be rated, hey, I only let the current go up to 30 degrees. So it could be that the one that was only rated for 1 amp, is actually the better choice. So some things to consider when you're choosing your inductor. All right, the goal is to get everybody feeling comfortable to design buck converters just as easily as they would design a linear regulator. And let me know if you want more information about linear regulators as well. Okay, hey, give a thumbs up if you like this, if you want to know more about buck converters, and give me a design example. Okay, like what input, what output, what current. Let's get a real design example. So give a thumbs up, be a subscriber with a design example, and I'll pick one and we'll put it in the next video. Okay, I'm going to do it real quick, so jump on it. All right, let me know if you liked the video. Hey, I want to thank my patrons for all the support. Thank all you guys for watching the videos. Give a thumbs up to the video. That helps YouTube analytics. Subscribe if you haven't done so, okay? Especially all you guys, I've been answering questions for a long time. Man, you guys seem like you watch a lot of the videos. I'm really thankful for that, but subscribe as well. All right, guys. Hey, we'll see you next time. All right.